Hello everybody, welcome back. So the goal of today is to derive the formula for the area of an ellipse in 3 different ways. So this is the problem at hand. We want to find the area of the region that's bounded by the curve defined by, well, x squared over a squared plus y squared over b squared equals 1. So yeah, we're looking for the area of an ellipse. And let's see what we're going to need in order to do this in 3 different ways. Okay, so first it looks like we're going to need some single variable calculus. For some this will be calculus 2, for some this will be AP calculus BC. It just depends on your course, what your institution calls it, but technically we're just using single variable calculus, and in particular the technique of integration by trigonometric substitution. Okay, well, we're also going to derive the formula for an area of an ellipse via vector calculus, and that's by way of Green's theorem. And then lastly, we'll use a little bit of linear algebra to find the area of an ellipse. Okay, so with that said, let's go ahead and use some single variable calculus to find this formula for the area of an ellipse. Okay, so let's start with some ellipse. It doesn't matter if my major axis is vertical or horizontal, so without loss of generality, let's assume maybe it's horizontal, so something like this. So there's A, there's minus A, there's B, and there's minus B. And so the equation is x squared over A squared plus y squared over B squared equals 1. So let's go ahead and solve for y so we've got something to work with. I could have just as easily solved for x. I'm just choosing y. So this is 1 minus x squared over a squared. I'm just going to multiply both sides by b squared. And then I'll take the square root. So y is equal to plus or minus the square root of b squared minus b squared x squared over a squared. And we can start to kind of exploit some symmetry of the curve here, right? Because, well, we know that the negative square root corresponds to this and the positive square root corresponds to this. So let's go ahead and compute just using the top half. And one thing we could do is just take the area from here to here and then double it. Or we could really use some symmetry and just compute the area from here to here and quadruple it. And so maybe we'll do that. That sounds like a nice game plan. Okay, so again, this will correspond to the positive square root, and then we're going to use symmetry and just take the integral from 0 to a, and then we'll quadruple it. Okay, so what does my integral look like? So we're quadrupling the integral from 0 to a, and again, that'll account for 1, 2, 3, 4 portions of the ellipse. And let's see what we have all together. Well, maybe I'll combine this into one fraction. I don't technically have to, but it might be nice. Let's see what happens. So this will be, looks like a squared b squared minus b squared x squared all over a squared, and that'll be dx. Okay, so that seems pretty good so far. And so let's go ahead and take the square root. So let's see what we're left with here. We've got 4 over a. So when I take the square root here, I don't have to worry about absolute values because of the interval. We're perfectly fine. So we're integrating from 0 to a. We've got the square root of, I'm going to call it, just for now, for a step or two, ab squared minus bx squared dx. This puts me in the form of a trig sub, which is kind of nice. Hopefully you recognize this as a sign substitution. That's how we're going to proceed. So in particular, we want to use this form here. We want to use this u is equal to k sine of theta, where this is u squared and this is k squared, right? So that means that u, so again, if that's u squared, then u is bx, and if this is k squared, then k is, well, ab. So there's my substitution. I'd like to maybe isolate x so I can find dx. So we'll say x is equal to a sine of theta, and then dx is equal to a cosine of theta d theta. So that seems pretty good. So I'm changing variables, right? I'm going from variable x to variable theta. So I also want to find corresponding bounds. So let's get some new bounds. So a new lower bound. This value of x goes in for x here. So 0 goes in for x, and then I just solve for theta. Let's see what that gives us. Well, 0 is equal to sine of theta, and so theta is equal to 0. And then I want a new upper bound. So a goes in for x, and I solve for theta. So a is equal to a sine of theta. That means that 1 is equal to sine of theta, and so theta is equal to pi over 2. So that seems nice. So now I can completely leave the world of x's and enter this new helpful world of thetas. Okay, so now we're integrating from 0 to pi over 2, again, in respect to theta. And then let's see what we have inside of here. Okay, well, maybe I'll go ahead and call this a squared b squared again. And then here we said x was equal to a sine. So together, think about what that gives you. That's going to give you a b sine of theta quantity squared. So when I plug this in here and then square it, I get the following. So I've got this a squared b squared sine squared of theta business. And then dx is equal to this. Got some nice interplay right here. Okay, so this is looking pretty good so far. So it looks like the a's are going to cancel, and I should probably think about factoring out in a squared b squared because we'll be presented with a nice Pythagorean identity. So a squared b squared, we've got that nice classic 1 minus sine squared of theta. Again, remember the a's canceled, so I just have this cosine of theta, d theta here, so that seems nice. And then let's see what we have here. So we've got 4 times the integral from 0 to pi over 2. And by our Pythagorean identity, we know that 1 minus sine squared of theta is, well, exactly cosine squared of theta. And since I have basically a monomial, in a sense, right, a single term under a square root, I could just take the square root of each factor. So that's going to give me a, b, cosine of theta. I don't have to worry about absolute values because of all the conditions on a, b, and cosine theta. They're all, well, non-negative. Okay, so a is constant and b is constant. So I've got 4ab. So that seems pretty good. And so that's going to give me a cosine to the first when I take the square root times another cosine to the first. So that's going to give me a cosine squared of theta d theta. And so exactly now we want to recall a power reducing formula. So in fact, let's just say recall that cosine squared of theta is equal to 1 plus the cosine of a double angle over 2. So we call that the power reducing formula, but it does come from the double angle formula for cosine. Very helpful here. Okay, so we have the following. So here, instead of cosine squared, by the power reducing formula, I've got 1 plus the cosine of a double angle over 2. Let's move that over 2 out here. So we can just say 2 goes into 4 twice. And we're left with the following. And let's move this up a little bit. Let's move this up. Okay, so we've got 2ab times the integral from 0 to pi over 2 times, or not times, but of 1 plus cosine of 2 theta d theta. And then we can just go ahead and integrate. Okay, so in respect to theta, the antiderivative of 1 is, well, it's theta. Here we need to be careful. So essentially I've got this like anti-chain rule. So I'm going to need 1 over 2, or 1/2, the antiderivative of cosine, and of course the same angle. Evaluated from 0 to pi over 2. But I notice that both of these terms will vanish at 0, so I only get a contribution at pi over 2, and in fact, I only get a contribution right here, because if I plug this into theta with our sine, that term will vanish. So I just have the following. Okay, so I'll have this pi over 2. When I plug pi over 2 in here, that's 0, and then both of these terms vanish at 0. And so we get the following. So we get a, b, pi. So that is the area of our ellipse. Okay, so our next goal is to take a journey into vector calculus. Let's see if we can arrive at the same conclusion but using a different technique. Okay, so let's just sort of briefly recall a bit of vector calculus. So I'm going to cheat a little bit. So you can look up the formal statement of the theorem, but I'm going to say if the region, the boundary curve, and these functions m and n are sufficiently nice, and what I mean by nice is R is simply connected, C is piecewise smooth, I travel the curve counterclockwise so that the region's always on the left, and m and n have continuous first partials. So if all of that happens, then we get the following. So then the line integral of m dx plus n dy is equal to the double integral over the region of these sort of rotation elements. This is the partial of n with respect to x minus the partial of m with respect to y dA. Okay, so here's maybe our nice piecewise smooth boundary curve C. We're traveling counterclockwise. Here's our region R, which is nice and simply connected. Okay, so without going into the details of this, what I want to know is, how can I think about this in the realm of area? So we need to recall something about double integrals from multivariable calculus. Recall that the area of a region R is exactly the double integral over the region R of 1 dA. Essentially what you're doing is you're taking the sum of all the area elements that are in the region, and that'll give you a total area. Okay, but if you look at this, we don't have an area integral, right? We have an integral that essentially finds the total rotation inside of R, right? It sums up all these rotation elements. So the idea is the following. If I can find a vector field so that this difference is 1, then this will actually be this. So let's note that. So if we can find a vector field, so f of x, y equals, we'll say m of xy, n of xy, such that the partial of n with respect to x minus the partial of n with respect to y equals 1, then we have the following. So then we have a line integral that computes area. But the key is to find such a vector field. In fact, there's tons of vector fields with that property. We just need to find one of them. Okay, so suppose we do have such a vector field, then this line integral is equal to 1 dA, or the double integral over r of 1 dA. But that's exactly the area of r. And so the classic choice of a vector field that has this property, and again, as I mentioned before, there's many that have this property, but the classic choice, or a classic choice, is this vector field. And you can verify that if you compute these partials and then take their difference, you're going to get 1, because you're going to get 1/2 minus 1/2, which is 1/2 plus 1/2, which is 1. So yeah, this is a vector field that satisfies this, which turns this into this. Okay, so this is exactly my m, and this is exactly my n. So I have the following. So I've got the line integral over c of m. So we said this was the m we're looking for. And that'll be dx, of course, plus n. We said n was, well, it's x over 2. dy. And we'll just factor out a negative 1/2. So that'll be y dx minus x dy. And this will be the area of our region R. Okay, so finally we've got this line integral from vector calculus that will allow us to compute area of a region. Okay, so what are we interested in? We are interested in exactly this. So what we want to do is take this boundary curve here and parameterize it or parametrize it. And so to do that, we could use the following, which is classic. We could say x is equal to, how about a? So based on this, a cosine of t. Y is equal to b sine of t. And you can verify by substitution that this equation holds because you'll get a Pythagorean identity. Okay, so this perfectly describes our ellipse, but I want to put a condition on t. Okay, so we've got a nice parametric description of this boundary curve here. And so we want to take this to the realm of our line integral. Okay, so let's use this. So playing the role of y is exactly this. Okay, so we're integrating from 0 to 2 pi based on our parameter t. Now y we said was equal to, again, b sine of t. Next I need dx, so I'm going to go and take the derivative of both sides. So dx is equal to negative a sine of t dt. Okay, so that's dx. Minus from the formula, and then x we said is equal to a cosine of t. And then next we need dy, so we're going to go here and, of course, take the derivative. So dy is equal to b cosine of t dt. Okay, so we've got our setup here, and we just want to do some algebra. So I think we can factor out a negative ab, if you take a look, right? Negative ab from here and a negative ab from here. And then these dt's, I think we can factor those to the right. So factoring out a negative ab from both terms here will give us double negatives, so that'll be ab over 2. the integral from 0 to 2 pi. And we're left with, it looks like, sine squared of t plus cosine squared of t dt. So that's pretty nice. Okay, so we just have the integral from 0 to 2 pi of 1 dt. But we know the integral of 1 is b minus a. So this is equal to ab over 2 times 2 pi minus 0. And that's a b pi. Okay, so very cool area via vector calculus through line integrals. Okay, so next we want to investigate a linear algebra technique to find the area of an ellipse. So with linear algebra, we want to think about sort of a starting curve and sort of shifting it or warping it in a sense via some linear transformation. So what kind of classic curve could I start with that I could sort of morph into an ellipse? Let's start with the unit circle. That's something that we could morph or shift into an ellipse via a linear transformation. So our starting figure will be the unit circle. Pretend that's a circle. And this region here, let's call this S. So this whole region here, we'll call this entire thing S. So that includes this. Okay, so the unit circle is what? X squared plus y squared equals 1. And what I want to do is, well, if I want to understand how a linear transformation works, I should really look at what happens to the basis vectors. Right, so let's take a look at the standard basis here. So here's E1. So as a column vector, that's 1, 0. And then this standard basis vector is E2. So E2. See, we're doing this live, folks. This is 0, 1. And what do I want to happen? So what I want to do to transform this into the ellipse that we've been talking about is, well, I want to stretch this, right? So instead of having length 1 here, it has length A. And then I want to stretch this so that instead of having length 1 here, I have length B. So that's my goal here. Okay, so imagine I apply some sort of linear transformation, and that's going to provide the stretch that we're looking for. Okay, so this, instead of being length 1, we want to stretch this so it's length A. And we want to stretch this so this is length B. Okay, and so here's our ellipse. And so if we want to write the matrix for the transformation, we just need to note the image or what happened to the basis, right? So this is exactly the transformation applied to E1, and that brought us from here to here, which is A0. And then right here, this is the transformation applied to E2, and that brought us, so the transformation applied to E2, that brought us to 0b. And so the matrix for our transformation will have this as its first column, and this as its second column. But that's exactly this matrix. So yeah, here's a matrix that represents our linear transformation. And so that starts with a unit circle, and we land at the ellipse for which we want to find the area. So now we have to recall something else from linear algebra. So again, if I'm calling this S, I'm going to call this the image of S under the transformation. So let's call this entire thing T sub A of S. So it's the image of S, the output under our transformation. Okay. So yeah, let's recall the following. So the area of the image of S, so the area of the image of S is equal to the area of S times the absolute value of the determinant of, let's give this a name. Let's call this A. Because that's a matrix transformation and it's referencing A, so of course let's call that A. So this is the absolute value of the determinant of A. Okay, so this will be the area of our ellipse. And so that'll be equal to the area of S, but that's the unit circle, so it's pi r squared. Pi r, because it's the unit circle, squared, times the absolute value of the determinant of A0, 0b. So that's pi times the absolute value of AB minus 0. And again, we get AB pi. Okay, folks, I hope you enjoy that. That's 3 different ways to find the area of an ellipse formula. So if you enjoyed that, make sure to give it a like, subscribe, share with your math friends, and I'll see you real soon. Take care, everybody. Bye-bye.